Hello. This is the third in a series of videos I've been doing about containers, like an introduction to Docker, an introduction to container orchestration, and then now an intro to Kubernetes. So together they should take you to concepts of how Kubernetes works at a basic level. If you already know Docker, you could probably skip the first one or two. And they are designed primarily for our recent interns, but I think anyone in the organization who is not super used to containers and Kubernetes will benefit from them as well. We have learned about in those first two videos. We learned about how Docker is leveraging Linux container technology to allow us to deploy stuff more easily, and it's easier because it is more portable in the sense that it encapsulates all of its dependencies within the Docker image, so that when you ship the container image from one host to another, you know that a different configuration on the host won't matter because all the dependencies and configuration is encapsulated within the image itself. It's more efficient because applications that share files, say they should share an underlying Linux distribution or a JVM or a node runtime or what have you, those shared parts can be not only downloaded once and only stored once. If you need to download multiple applications that use them, you only download those bits once. So it just means it's more efficient use of network bandwidth and of storage, and hence reducing your costs. And as I said, it leverages Linux container technology, which brings us some isolation. It's not the same amount of isolation as we get with VMs, it's less, but it's a trade-off for the speed and scale and the sort of resource utilization that we get with containers versus VMs. And Docker is really cool. It's really a great way to learn about containers and allows you to get started quickly without understanding the low-level details about how Linux containers work. It's got a great user interface. However, it's you need to get beyond beyond single host to multiple hosts. To have a distributed application, you're going to need some sort of container orchestration. Given we're watching an intro to Kubernetes video, no doubt the no surprise that the container orchestrator that I'm talking about is Kubernetes. It's the one we use here at Influx. And the kind of jobs that a container orchestrator does when we move to multiple hosts is scheduling of containers, which hosts should they run on, allowing some network connectivity between the containers running across multiple hosts, server discovery and load balancing for those services, those applications, and centralizing a logging and monitoring so that you can ask the cluster for logs without having to SSH onto each host, and you can have some central place to see what's running and what's not running. Okay. Alright, so let's look at some core concepts of declarative configuration, resources, and controllers. So when we think that we're going to when we think about deploying something onto Kubernetes, say we have some application and we want to deploy it onto Kubernetes, we shouldn't really think of that as an imperative operation, but rather as a declarative one. What do I mean by that? So instead of saying start this container, start that container, change the setting to this, change the setting to that, these are very active commands, the directives. Whereas with declarative configuration, we tell Kubernetes, I want there to be 5 of these running and have them configured in this way. And then Kubernetes works to make that so. And the things that we're declaring are resources. We'll learn a bit about the different kind of resources, but you can think of them as our workloads. Ultimately ends up with running containers. And the component that does the reconciliation of desired state and current state is are called controllers. So if we take, for example, this case here in the diagram where we've said desired state is 6 replicas, we tell Kubernetes that it gets stored in its data store, and then at some point the controller is looking to see, is the desired state currently being met? oh, there are only 5 replicas, what should I do about that, and go and take some sort of action. It's important for Kubernetes to work this way with this declarative configuration and the controller loop rather than imperatively. It can't just set and forget what you ask it to deploy, because in a large cluster with many applications, it's the only scalable approach. Node loss occurs, apps crash, apps get rescheduled, the network is unreliable. So keeping things in sync is a constant job. And that's why Kubernetes has this design of controllers that reconcile desired state with current state. So this desired state, we tell Kubernetes what we want the current state to be, and that gets stored in its data store, which is called etcd. Kubernetes is constantly monitoring what is currently running and also storing that in etcd. So the controller you can think of as grabbing information out of etcd, and then performing some analysis on that, and then taking actions in a loop. I've seen it called observe, analyze, act. So there are some other models for it, but it's a control loop. It may seem to you that it's a kind of a deep dive right away into some low-level functionality of Kubernetes, and I suppose it is in some levels, but I want to bring it forward as part of the core concepts, because once you understand this controller loop and declarative configuration nature of Kubernetes, then it will really serve you well going forward. The rest of these slides aren't that low level. Again, this concept of imperative versus declarative, if you've ever done something like work with computer graphics and heard of like immediate mode versus retained mode, it's a similar concept, and probably in other parts of computer science as well. If you've had some basic exposure to Kubernetes via kubectl, you're probably not even aware of the existence of controllers, but it is the controllers that are making the cluster work behind the scenes. And yes, as I said, they work by gathering information about the current state, comparing it to desired, and then taking action. So, for example, we want to deploy a new application. We declare to Kubernetes that we want 5 instances of some application with some set of configuration. Let's say 6, because that's what we've got the diagram here. The controller then compares the desired state with the actual state and sees, okay, we should be having 6, but we only have 5. And then, okay, let's create another replica. In order to replace the one that is evidently lost. Okay, so we talked about resources at a high level, saying resources are your workloads, and Kubernetes control loops are observing the resources that are running versus what you've declared and reconciling them. So there are actually a number of different kinds of resources. We're going to dig into a few of them. This list here is a subset of the core resources. So Kubernetes comes with a bunch of resources built in. You can also extend it, but we're not going to go into that here. This list is a long way from being a complete list of core resources, but I think it's the important ones to get your head around at first. So pods are the unit of scheduling and execution in Kubernetes. When you might think that you're asking Kubernetes to run containers, and ultimately you are, but the lowest level that Kubernetes works with these things is called a pod, and it is one or more containers that are scheduled together on the same host and share a network namespace. So you may remember from the first video about Intro to Docker, about C groups and namespaces are the Linux technologies that make containers work. Namespaces are the feature that give you some resource isolation at the kernel level. So, and network namespaces do that for networks. So it means that each container has its own view of the network. It thinks it has localhost and it's the only one on the machine and can't sniff anyone else's traffic. So one or more containers that live in the same pod and share a network namespace. That means they are all using the same network interface. You couldn't have 2 containers in a pod binding to the same port, for example. It's the same interface. If that's all a bit low level and technical, most of the time as a developer you're thinking of running 1 container per pod. So you can think pod equals container. It's not strictly correct, but it's close enough for a high level view. So what are the kind of reasons why you might want to have more than 1 container in a pod? It's generally for operational reasons. It's not often something that an application developer would think about. So things like logging or monitoring agents. So another container that sits in the same pod, grabs log files and ships them off to some remote service. That a Kubernetes pod doesn't necessarily need to have a logging agent, but it's an example of something you might want to do. Or perhaps you have some fast in-memory cache that you want to run. It has to sit on the same host. If it's scheduled onto a different host, and you have to make a network hop across the host to talk to it, it wouldn't make sense. You might want to there might be a case where you'd want to schedule that in-memory cache as another container in the same pod. Okay, so let's look at some examples on the command line. So here on the left, we have a YAML file for a pod. When we declare resources to Kubernetes, we do it via YAML. And some key things to pick out here is kind pod. All things that we declare in Kubernetes have a kind and an API version, but let's not worry about that right now. So kind pod is important, and then the spec of the pod needs to follow a particular schema, and indeed this one does. It's going to run one container with one entry in this list, called API, running this Docker image and exposing this port. So here we are. I have kubectl pointing to a local cluster. You can see that I have no pods currently. I can do kubectl apply pod.yaml, which is the one on the left there, and it will say pod created. And then when I do get pods, I can see that it's already running. We have our pod. It's a little faster than usual because I've sort of rehearsed this, so it's kind of cached. But it takes as long. It should take as long as it takes to download that Docker image, basically. I can also do kubectl get pods will list all the pods. I only have one at the moment, but kubectl describe pod API will give me more detail about one particular pod. So we can see in here, it's got various bits of information like when it was launched, its status, its IP address, the image that I gave it, and then once it's downloaded it and got the full SHA, it's expanded that information. Various bits of information about ports and a bunch of stuff we don't care about here, but some events in its life cycle. It got scheduled to the one host my cluster has. It started pulling the image, it finished pulling it, it created the container, it started the container. And here we are again, get pods. We see that it's running. Okay, so pods don't really have a life cycle. This is a limitation of them. They get created, they go into running status, and when the process completes, whether it be because it exits 0, i.e. healthily, like it was like a batch job, or it's a long-running service and it crashed at some point, however that happened, Kubernetes will remove them. It's not really a concept of restarting a pod, at least not strictly speaking. So this API here is a long-running service. It's an API, so we don't want this to when we need somebody to keep it up. So what if it was an important service and not this demo API thing? When it crashed, wouldn't we want Kubernetes to restart it when it crashes, right? I think we would. We'd want to guarantee some sort of upness of it. So even if we only have one instance of it, we want it to always keep one. And we talked earlier about the declarative configuration of Kubernetes. We would like to be able to say we want one and for you to keep one or more running. So for that we need a replica set. And a replica set is a way to describe to Kubernetes one or more identically configured pods. And we have an example of one here. Replica set. This is a replica set for the same running the same application as the pod was. So we see down here containers. There's one container. We put some labels on it, and the one key difference that we have in a replica set that we don't have in pods is this replicas 3. So that allows us to launch more than one and to keep them running. So let's delete this API, and sometimes that takes a while to complete, and never mind that. Control apply. Let's create this replica set that was specified on the left. So what this is doing is saying to Kubernetes, I want 3 replicas of this demo API now. And here we see that that's created. Get replica set. So desired 3, current 3, ready 3. That's cool. Let's do get pods again. We see that this our one from earlier is still terminating, but probably if we run this again soon, it'll be gone from the list. See, there you go. So now we have 3 instances of API. They all have this suffix minus and then some generated 5-character name. So here we start to see evidence of the fact that replica sets manage pods. But let's see this again. So we've got 3 there. So what do we think will happen if we were to delete one of these? Have a think about that. Remember that we have previously said to Kubernetes, create a replica set of 3 replicas of this particular pod. Here we're not changing that instruction. We're just acting as if one of these has been killed or has crashed or something like that. I'm going to run this in the background again and put a watch on get pods, and we can see that 14 seconds ago a new one started whilst I was faffing around there trying to set up the watch, and we have the one that we originally created is on terminating. I think this is taking so long because the application doesn't respect the Unix signal that should tell it to gracefully kill, and then Kubernetes will eventually kill it. Okay, so now we have 3 again. So this replica set feature resource is what gives us the kind of the idea that you can tell the cluster how many instances you want of something running, comfortably go home for the weekend, and know that Kubernetes will at least try and keep that many running. Even if your application crashes and runs out of memory now and then, it'll come back. So you'll have some instability if your application is crashing all the time, but it will stay up. All right, so let's just have a closer look at the replica set here. We can run describe, and we can see all the things that we specified here before. The 3 in running state, and the operations it did to create 4 pods over the course of time. So this is the one where we deleted the first one, then it decided that it needed to add another. So in the background, what was happening there is that is a component called the replication controller, or the replica set controller is doing this observe, analyze, act loop. It's looking at the desired configuration, the current configuration. It noticed that there were 2 pods instead of the desired 3, and it created another one. Okay. What do we think would happen if we had a multi-node cluster and our 3 pods were spread across the nodes, and then we deleted one of the nodes? So we're down to 2 hosts and 2 pods. I'm not going to demonstrate that because I only have 1 host here. But what it will do is the controller would notice that there are 2. It will create a new one, and then the scheduler, we'll talk about that later, will decide where to put it, and it won't put it on the now missing node because it's gone. So you'll end up with 1 pod on one host, 2 pods on the other host. Okay. So as I said, ReplicaSets manage pods. We are able to instruct a replica set to change its number of replicas, and that will add and remove pods for us. We don't need to create and remove the pods. Now have a think about how we would roll out a change to our application. So I've said here it's on v1. Let's imagine we make some new feature and it's now at version 2, and we want to roll that out. How would we do that with a replica set? We can't change the replica set to, like, we can't just say do this now, use this new image. Well, arguably we can, but just trying to think through this as an exercise. Would we want to delete the replica set and create a new one with version 2 image, or would we want to edit the replica set, which we can do technically, and change the image name, or would we want to create a new replica set and then delete the other one? I think the last option is probably the safest. We'd end up with double the number of pods for a moment, and then we can just, once we know that it's healthy, we can start to remove the old ones. Or maybe create a new replica set for the new version with only one replica. When it's healthy, scale down the old one and scale up the new one, so we've still got 3. And eventually on this process you'll end up with 0 on this replica set and 3 on the other one. That's a neat pattern, and in fact Kubernetes has something built in to do this for us, and it's called a controller, and it's a new resource called a controller. It's not new in Kubernetes, it's new in these slides, called a controller, and it manages replica sets in the same way that replica sets manage pods. So it creates each new deployment will create a new replica set and manage the transition between them by scaling them up and down, and it's managing that transition by a controller, as I was saying. So here we're looking at a situation where we're moving from having v1 to having v2. So I've got these little arrows in some of these boxes here. So we're going to start off with a deployment on v1 and 3 replicas. That's going to create this replica set and these 3 pods. Then at some later point we edit their deployment and say image is now v2. It's going to create a new replica set for version 2, and it's going to start to scale this one down and this one up. So this is going to move from 3 down to 0, and this from 0 up to 3. Okay, so let's have a play with this. Here we have another document, looks very similar to the other one, but now it's called deployment, otherwise it's the same. Have I deleted the pods? Yes. Cube control apply -f deployment. So this is going to create a deployment which will create a replica set which will create 3 pods. Okay, so let's do get deployments. We see 1 deployment, there are 3 of them, and they're ready. It comes up really quickly because this host has already downloaded the Docker image, so it doesn't take very long. Let's look at the replica sets. We see that there is one with a generated name which has been created by the deployment. So a deployment called API will create a replica set called, with some longer name. Just as earlier I forgot to say, creating the replica set called API would then lead to pod names with the replica set name prefix and then some generated suffix. So as you might guess, when we do get pods, we're going to see prefix by the replica set name and then a generated pod name. Cool, so we have 1 deployment, 1 replica set, and 3 pods. Okay, so now what I want to do is edit this deployment and make some change so that we can then see what it does for us. So we're going to add an environment variable. This is just something to trigger a change in the deployment. So contrived example, of course. But this demo API service happens to take this environment variable. I can now do kubectl apply, and what we're going to see is, well, have a think about this. Remember what we said here on this slide about what deployment does? We should expect to see something like this, right? A new replica set that will start to be scaled up as the other one scales down. Alright, so we see here 6 pods, 3 running and 3 terminating. That happened all quite quickly. And if we get to replica sets, we see 2 of them, one of them older than the other, and now on 0 instead of 3. And one deployment still that has managed the both of them. So this deployment has created this replica set, which has created these pods. Because you can see here this prefix 7754 is the new one. All right. Now, if we do kubectl logs this, it won't have a message because we haven't made any requests to it. So I'll just show you that, for example. So let's use a feature that we're not discussing yet. Import forward to pod. I've still got a port forward running somewhere, have I? I have. Okay, so port forward. Now I can curl localhost. Don't worry about the details of this. I just want to show you that I can hit that service on that pod with. I can hit that service with that pod with curl, and I will get this message that says new version. So you can see that the message has rolled out. Okay. Now, if we return over here for a moment, so where replica sets have a controller that manage pods, deployments are a controller that manage replica sets. The controller creates a new one each time and increases the replica count while reducing that of the other. So if you were to watch, some graph over time of number of instances of pods, you'd see the whole value constant, but you would see old versions going down and new versions going up during a deployment. And this whether it will add one of the new one and then remove one of the old one, or remove one of the old ones first and add one of the new ones second, this is tunable. Whether you want it to add 5 at a time or 1 at a time, that's tunable. You can also have it just completely blow away the old one and add the new one. But nevertheless, the deployment controller is the one that's managing those transitions. Okay, now we're going to explore some basic Kubernetes networking in order to learn about the next resource called services. So this is where we have one kind of service that wants to talk to another. So I don't know, like a customer API wants to talk to a bookings API or a payments API, these kind of things, if you think it's an online shop of some kind. We talked in the earlier video, the first video, or no, the second video, about service discovery and how we need our container orchestrator to help us with this. So if we have service A wants to talk to service B, we can't, if there are multiple instances of service B, we can't be having service A having to know about the IP addresses of all 3 of them and doing some sort of client-side load balancing. What we want is to be able to talk to a service by service name, i.e. DNS, and have the container orchestrator keep that DNS entry up to date as pod IP addresses change. Well, more accurately, as pods come and go and the new ones have different IP addresses. Okay, so we can use what's called a Kubernetes service. It's a new kind of resource. Again, not new in Kubernetes, just in these slides. So we've learned about pods now, ReplicaSets, deployments, and now services. You can think of a service as providing service discovery and internal load balancing for our services. It's not a software component like a proxy. It's not like Nginx or HA proxy. It's just a piece of configuration that Kubernetes will then use to dynamically reconfigure the networking to make sure that DNS request can resolve, and that it will resolve to an IP that's routable to those pods. The details of how this works is not really something I want to go into here, but if you know about Linux networking interfaces and IP tables, so Linux firewall rules, it works like that. Okay, so let's jump back here again to our next example, and here we have another Kubernetes YAML file called a of-kind service. We can see here also that we don't have any services. Oh, yes, we do, because I was testing this earlier. Get services, all we see is Kubernetes, which is the Kubernetes API. Let's not worry about that for now. Okay, so going to do kubectl apply -f service.yaml. So now we see a new service, and let's describe it for a bit more information. So a few things that are interesting here. We have our selector app equals API. This relates back to all of our pods that we create. They get this label app API, and it's via those labels that Kubernetes knows that this service should be sending traffic to those pods with that label. It's of type cluster IP. There are various other kinds, but this basically means that we're going to have service is going to have one IP address. It is going to be that. The name API will resolve with DNS to this IP address, and it's going to be on port 80. So we can do kubectl port forward service API. Hold on a moment. We can. Oh no, I'm going to do this a bit differently. Let's come back to this. So we did that. We did that describe here. The other thing I want to talk about before I show you that is these endpoints thing. So other services will be talking to this service with something like this, right? Or with the domain name API, won't need to specify the port because it's the default. And but it's going to direct the traffic onto the API pods on port 9000. So it's okay for these ports to be different. And then we have these things called endpoints, which are similar to like an Nginx backend, if you've had some experience with that. They are the endpoints that are going to fulfill the requests that are coming into this service. So we would do a request to this, but we would end up arriving at the IP address of one of these pods. If we list our pods here, we'll see that these IP addresses are the ones that are listed here. Okay, so I'm just going to run another image that has curl in it. Okay, so here we are inside another container in the cluster, another pod in the cluster that I've created just so that I can make requests to the API. So, and I have curl installed here because it's a curl image. So I can make requests to the API, and you can see that over time the load balancing is not strict round robin, but more or less these pods are reporting back their IP address. So yes, I was able to. So that means that this has a DNS entry that resolves to something that routes to that. See this here, 10.105.161.176. That is the cluster IP address of our service. We can also kill that, and it will work. It does the same thing. So Kubernetes is dynamically configuring Linux networking and IP tables to make sure that when after resolving the DNS and making a request to this, that it will get routed to one of these. Okay, so that's their services. You might think, well, why do we need a separate resource for service? Why shouldn't all pods just get a service by default so that we have service discovery and load balancing? That's because we might use pods for other things, such as things that are not services, that don't listen and so on ports and serve traffic, that are like maybe batch jobs and things like that. Finally, I'm just going to cursorily cover config maps and secrets to round out the list of the most common core resources. They're effectively ways to get configuration into your application. So we saw earlier an example of me specifying an environment variable in a pod. So that was this one here. In our spec for the pod, I added environment variables, but we might also want to add configuration files, or have some values in a file that we can set then as an environment variable, or various combinations of these things. But we've got lots of ways we want to be able to provide configuration into our applications, and config maps are the primary way of doing that. We also have secrets, which are effectively the same thing, except they get encrypted before they get stored into etcd. Alright, just have a quick recap. Pods are we have everything in Kubernetes we configure declaratively. Kubernetes uses control loops to reconcile desired state with with current state. And we have these core resources. Pods are the unit of execution, but they have no lifecycle. ReplicaSets are one or more identically configured pods that we can use to maintain some service level, so keep one up or two up, that kind of thing. Deployments manage ReplicaSets by transitioning between versions as we release more versions of our application over time. And services provide service discovery and internal load balancing. Config maps and secrets both allow you to configure your applications, but the latter are encrypted. If you want to have a play with some of these things, a number of ways you could do it. One is to go here to Katagoda and follow some, which is a sort of an online in-browser, terminal in-browser type learning environment. They have some training scenarios around basic Kubernetes stuff. You can go and have a play there. There are a few of them that are about creating clusters. You probably don't need to worry about those, but go to basic use of kube control and networking and these kind of things. Check them out. You can also check out the Kate's IDPE repository. It's managed by the deployments team. In the README there, you'll find some instructions on creating a local cluster. And yeah, thank you for listening. Of Kubernetes work, like the API server and the scheduler and kubelet and whatnot.